we start? Okay. All right. Well, it's still a pleasure to be here. The pleasure grows with every week. So this is my second week here. So we have another talk. And this time I'm going to talk about solid forms of quark matter. So let's get started. So the outline of the talk, this really wants to be here, doesn't it? Okay. The outline of the talk is, firstly, I'm going to give the broader context of where you find quark matter, and that's hybrid stars or strange stars. So I'll review that physics. And then I'll talk about the possible phases of quark matter that might be described as solid. And so the ones I'll talk about are the crystalline color superconductor, a mixed phase, which people sometimes call in other contexts pasta, at the boundary between the nuclear matter and the quark matter regions of a star. And then the third one I'll talk about is a possible strange crust on a strange star. Okay, there's another possible solid phase that I'm not going to talk about, which is a thing called the chiral density wave, or the Deryakin-Grigoriev-Rubikov phase, or the quark-ionic chiral spiral. There's different names for that one. I'm not going to talk about that. So then I'm just going to go through the three that I am going to talk about. First, the crystalline color superconductor, which people sometimes call LOF, or they flip them around to be FFLO, which apparently the official pronunciation is Fuffalo. And then I'll talk about another possibility, the mixed phase at the nuclear quark boundary, and then finally the strange crust on a strange star. So I'll just go through those three possibilities. All right, let us start then with the broader context. Where are you going to find quark matter in neutron stars? And there's two basic scenarios. The conventional scenario, shown on the left here, is a neutron star or a hybrid star. So the neutron star, which doesn't have quark matter, is just nuclear matter all the way to the center. And at the surface, there's a crystalline phase, which is a nuclear crystalline phase. It's a bunch of nuclei arranged in a lattice with electrons around them. Now, one way you can get quark matter is if the middle of the star gets dense enough, then you may get quark matter in the middle. I'm calling that SQM, strange quark matter, and that's called a hybrid star. So this is one place you might get quark matter. But then there's another scenario, which will be relevant for some of what we're talking about today, and that is this thing called the strange matter hypothesis, going back to the 70s and 80s, where you have a thing called a strange star, which is strange quark matter in its entirety. Now, there's various forms that a strange star can take. You can just have a bare surface here where the strange matter ends and then there's just vacuum outside. You can have a nuclear crust on a strange star. So the idea there is you have all this quark matter, and then the quark matter comes to an end, but because of the, we'll get to this later on, but because of some of the characteristics of the quark matter, in particular the strange quark mass, there's some charge at the surface, which creates an electric field, which repels nuclei that come up to it. So if you gently drop some nuclear matter onto this strange star, it might stay on the surface, suspended on an electric field, and you'd get a nuclear crust. The thing I'm going to talk about is an analogous possibility where, suspended on the surface, instead of having ordinary nuclear matter, you could have a sort of crystal made of strangelets, little chunks of strange matter. So basically, they're like little droplets of the stuff that the whole star is made of. So this is these are the two scenarios in which we can have quark matter, and the different solid phases I'm going to talk about are more or less, important in one or other of these scenarios.
Strange quark matter is locally neutral, right? Charge neutral. So why you?
Yes, in bulk it is, but locally at the surface it may not be. Okay, because so what happens is, it depends on the strange quark mass. If the strange quark mass is 0, then just ups, downs, and stranges are neutral. Okay, and then nothing interesting happens. There's nothing at the surface. But if the strange quark is heavier, then you need some electrons to make the quark matter neutral. And then at the surface, the electrons have a longer tail of density, right? The electrons leak out into the vacuum, and that creates an electric field where the surface of the quark star is deprived of electrons, and there are more electrons outside, so that makes an electric field. Does that answer the question? Okay. All right, so let's go through our different forms of solid quark matter. Oh, sorry, no. Before I do that, I got to do, this is the sort of picture of the two scenarios. Now I'm going to do the thermodynamic description of the two scenarios, which we'll come back to later on, but I want to have it out there. So this is a plot of pressure against quark chemical potential. And the conventional scenario, where you have vacuum going to nuclear matter, going to quark matter, is where the pressure as a function of chemical potential looks like this. So for nuclear matter, you have a curve like this. And for quark matter, you have a curve that comes up and intersects it at some positive pressure here. So if you ask what's the favored phase at any given chemical potential, at low chemical potentials, you have the vacuum. When the chemical potential for quarks reaches 310 MeV, so that's enough energy to make a bound nucleon, then you start getting nuclear matter. And then if the density and pressure get high enough, there's a critical pressure where you get a transition to quark matter. It's always the phase with the highest pressure at a given chemical potential that wins. So that's the favored phase. So this is how those curves look in the conventional scenario. Now, in the strange matter hypothesis, this red quark matter curve is shifted upwards. So you could say that's a smaller bag constant if you want to use that, terminology. And so now, if you ask at any given chemical potential, what's the phase with the highest pressure? At low chemical potential, it's vacuum. But then at some critical chemical potential, you get a transition straight to quark matter. And nuclear matter never gets any attention at all. It's always a disfavored phase. So the strange matter hypothesis says that actually nuclear matter is always metastable, and the truly favored phase is always quark matter once the chemical potential gets high enough. So these are the two scenarios. In this second scenario, you can get strange stars where it's strange all the way to the surface where the pressure reaches 0. In the conventional scenario, you only get quark matter at high enough pressures, so you would only get it in the core of a neutron star. So this is the thermodynamics behind those two scenarios. And it's just a matter of where this quark matter curve is, and we don't know where it really is, because we don't know very much about quark matter. We'd have to solve QCD at finite chemical potential to know that. We can't do that. Okay, so this is the big picture that we're operating in. Now, let's start with the first example of a solid phase, and that is the crystalline color superconductor. So for this, I'm going to review a little bit of what I talked about last time. So last time, I talked about color superconducting quark matter, that as you fill up the Fermi sea with quarks, which is a dense system of degenerate quarks, if there's an attractive interaction, that makes it favorable to create Cooper pairs at the Fermi surface here, Cooper pairs of particles above the Fermi surface, Cooper pairs of holes below the Fermi surface. And this is true not just for quarks, but any system of fermions that form a Fermi sea like this. And I'm assuming the temperature is low here, so this Fermi surface is not thermally blurred. And so, as I discussed last time, you get a BCS state, which is the favored state thanks to the attractive interaction, where in each momentum mode above the Fermi surface, you have some amplitude to make a Cooper pair of quarks with equal and opposite momentum. And in each momentum state below the Fermi surface, you have some amplitude to make a Cooper pair of holes with equal and opposite momentum. And you construct this state by operating on the Fermi sea with these operators. You choose these coefficients here to minimize the energy, and you find a new ground state that is lower in energy than the bare Fermi sea because it exploits the attractive interaction. And the one that exploits the attractive interaction best is the favored state. So that's what's going on in a color superconductor. And also what we discussed last time was if you have three massless quark flavors, so the up and the down are pretty much massless, the strange quark, not so much, as we'll see in a second, but if you're at very high density where the strange quark mass could be neglected, you would get this color flavor locked phase up here at the highest densities, and it has this interesting structure, antisymmetric in color, antisymmetric in flavor, in a correlated way between the colors and the flavors. Color antisymmetric, space symmetric, spin antisymmetric means flavor antisymmetric. So the most favored phase wants to pair different flavors with each other. If you want to have something that's antisymmetric in flavor, which is what we expect to be most favored and what calculations tell us is most favored, then it's going to be, if it's antisymmetric in flavor, it has to involve two different flavors, like strange up minus up strange. And if they were both stranges, this would be zero. You couldn't have a flavor antisymmetric wave function if you had only one flavor. So the key point here is that the most favored forms of Cooper pairing tend to involve Cooper pairs of two different flavors. Okay? All right, so with that in mind, let's now move ahead and think about supposing that we try to be a little bit more realistic and say that we don't have three massless quark flavors. So, this is another way of looking at that, that pairing pattern. You can write it as a matrix in color flavor space, but okay, that's just for fun, kind of. So in the real world, things are a little bit different from that idealized world of three massless quarks. There are some factors that make pairing between different flavors more difficult. Even though it's the channel that's most energetically favored, there are some other factors that, that make it less easy to do. And this comes down to the strange quark mass and electrical and color neutrality. So the strange quark mass is not zero, which is what I was assuming on the previous slide to get the color flavor locked pattern. And it's not infinite, which would be another nice limiting case where you could just ignore it and say we have two flavors, and we look at two flavor pairing patterns. It's right in the middle where you kind of trip over it. It's I'm talking about a sort of effective constituent quark type mass here, so the mass that includes the chiral symmetry breaking contribution. And in the vacuum, that's about 500 MeV. And at high density, the chiral symmetry breaking contribution becomes less or goes away depending on the phase. And the strange quark mass drops to about 100 MeV. But either way, it's right there in the same range as your chemical potential for quarks, which is about 300, 400 MeV. Okay, it's about 1/3 of the chemical potential for baryons. So, and it's about the same actually as the confinement scale of QCD. So it's really right where you don't want it, right? That you have no separation of scales that you could use to deal with the strange quark mass. And so, okay, so the strange quark mass isn't zero. It's right about the 100, few hundred MeV range. Second thing you have to take into account, if you want to be more realistic, is electrical neutrality. Quark matter in a neutron star is not like quark matter in a heavy ion collision. In a heavy ion collision, you don't care if there's electric charge around. But in a neutron star, you've got cubic kilometers of this stuff, and you can't have cubic kilometers of charged material. There'd be huge electric fields, and it would be energetically very disfavored. So it neutralizes itself. It gets electrons or whatever it takes to be neutral. So quark matter in the sort of bulk that you find in neutron stars should be neutral with respect to all the gauge charges, electromagnetism and color. And then finally, the final factor that comes in is flavor equilibration. So again, astrophysics is different from heavy ions. On astrophysical timescales, you have weak interactions that equilibrate the flavor content. So they will convert downs into stranges or ups into downs and electrons and ups into downs or whatever you want. So these three factors together mean that you're not going to have the same density of all three flavors. Okay, the strange quark mass is going to be, there's going to be less of them. So let's see why that is. So So here we go. So let's look at this plot on the right here first, which shows, just imagine one quark, and here is its momentum along the bottom, and here is its energy up the side. So these curves are dispersion relations. They're just the energy-momentum relation of a quark. So for a down quark or an up quark, it's pretty much massless, so its energy is equal to its momentum. You get this nice straight line for the energy-momentum relationship. For a strange quark, if it has a mass, then its dispersion relation starts up here, where the energy is equal to its mass when its momentum is 0. And then as you add more momentum, its energy goes up, and eventually it asymptotes out to something similar to the massless guy. Okay, so downs and stranges. Let's consider downs and stranges for now. The strange is massive, the down is not. But they have the same quantum numbers, right? As far as quantum numbers are concerned, things that couple to conserved charges, they have the same conserved charges. They have the same baryon number, 1/3. They have the same electric charge, minus 1/3. Okay, so there's really no difference between an up and a strange quark as far as conserved quantities go, and that means they're going to have the same chemical potential, which means they're going to have the same energy, Fermi energy. So the Fermi energy is here, all right? And since the strange quark has a mass, its Fermi momentum, the momentum of the last filled state before we get to unfilled states, is going to be different from the Fermi momentum of the down quark. It's going to be less. And the reason is strange quarks are more expensive, right? Each one costs its mass before you even put in any momentum. So because of the strange quark mass, there'll be fewer strange quarks. So you see that here, we filled the strange quarks up to their Fermi momentum. We filled the down quarks up to their Fermi momentum. They both have the same Fermi energy, but they have different Fermi momenta. And this is because of the strange quark mass. And if you ask, what's the difference between these two Fermi momenta? If you assume the strange quark mass is not too big, then you can expand and you find that it's about strange quark mass squared divided by twice the chemical potential of the quarks. So there's this splitting between the Fermi momenta caused by the strange quark mass. This is before you do any pairing, right? This is if you're just filling up the Fermi seas and you're ready to start doing Cooper pairing, but you haven't done it yet. Okay, so why does this matter? Well, it matters because, as you remember, when we formed Cooper pairs, we formed Cooper pairs of quarks that were at their Fermi surface, so they didn't cost any free energy. Their Fermi energy was equal to their chemical potential, and they had equal and opposite momentum. But you can't do that in this case. If you look at a strange quark on its Fermi surface and a down quark on its Fermi surface, you can't give them equal and opposite momenta. Okay, they can't have 0 net momentum. It's not possible because the strange quark's Fermi momentum is smaller. So you have this sort of battle. So remember the mismatch goes like ms squared over 2 mu. Let me go back to the previous slide a second. The mismatch goes like ms squared over 2 mu. So if you turn up the density really high, then this isn't going to matter anymore, right? If the density is really high, then the Fermi momenta are going to become similar again because the strange quark mass is negligible compared to the Fermi energy. But if you're at lower density, then this becomes more noticeable. The splitting gets bigger. So what I have on this page here is, so high density, sort of middle density, and low density. So at high density, this ms squared over mu quantity is not so big, and the Cooper pairing can overcome it. Roughly speaking, if the mismatch between the Fermi momenta is smaller than the gap you would get if you did the Cooper pairing, then the Cooper pairing doesn't care. It goes ahead, and you still lower the energy. So actually, maybe I should start on the left here with the unpaired case. So with unpaired quark matter, the downs and the stranges are split apart because the stranges are heavy. So you can't have so many of them. So you have to have a smaller Fermi momentum for them. But you have to be electrically neutral, right? So the ups, the number of ups is roughly speaking halfway between the downs and stranges because you want to compensate for the charge of the downs and the charge of the stranges by using up quarks. So the splitting between the downs and the stranges was ms squared over 2 mu. The ups go in the middle to achieve electrical neutrality, And so the splitting between the downs and the ups and the stranges is ms squared over 4 mu. And if the Cooper pairing that you would get from pairing downs with ups or ups with stranges is bigger than that discrepancy, that difference in Fermi momenta, then the pairing can still win, right? It costs a certain amount of more energy because it's trying to overcome mismatched Fermi momenta, but it can still do it. So as you turn the density up, this mismatch gets smaller. And so at some point, maybe you can just pair two of the flavors, like this is up-down pairing, and eventually you can pair all of them. And the Cooper pairing pulls their Fermi momenta together and then pairs them, is how it works.
If you have electrons, then
yes, the electrons are in there too. The electrons don't make too much difference to this, but yes, I'm roughly speaking, it goes the way I said. But yes, you should include electrons. But you still get this sort of series of changes from at lower density, the splitting is too big for the Cooper pairing to overcome, and the highest densities, it isn't so big anymore, and the Cooper pairing can overcome it. So at the highest densities, you'll still get the color flavor locked phase, but at lower densities, you might get something else, because as you reduce the density and this ms squared over mu parameter gets bigger because mu is getting smaller, it becomes harder and harder for the CFL pairing to win. And so you may find something else winning. And one possibility is some two-flavor pairing. There are other possibilities with kaon condensation, but the possibility and color spin locking and all sorts of interesting things. But the one I'm going to talk about, one of the ways in which the system might say, I want to pair, but I can't because the Fermi surfaces of the quarks are mismatched. How can I still do some Cooper pairing? Because Cooper pairing, if you do it right, lowers the energy. How can I still do some Cooper pairing? One of the ways it can do it is this crystalline or Loff phase. So let's look at how the crystalline or Loff phase fights back against this mismatch of Fermi surfaces. So are there anybody want to ask a question at this point? Now I've got to the sort of main point of what I'm doing. Any questions? Any questions online? No, we're okay. All right, good. So let's get on to this question. How does some sort of crystalline phase help overcome this mismatch of Cooper, or this mismatch of Fermi momenta? So the crystalline phase basically looks like this. It says, okay, I can't pair any old quark on the strange quark Fermi surface with any old quark on the down Fermi surface. Their momenta won't add up to 0. So I'm going to have to face the fact that my Cooper pairs are not going to have equal and opposite momentum. So how could I do that in a reasonably coherent way so their energies add up nicely? And the Loff suggestion is, supposing you take a ring on the down quark Fermi surface here, and you pair them with particles on a ring on the strange quark Fermi surface, such that the x and y components in the horizontal direction cancel out, that the x momentum of the strange quark cancels the x momentum of the down quark, but the z momenta don't cancel. So in this case, the center around which these momenta would look equal and opposite is displaced by this little momentum q. So basically, each quark has momentum q sort of for free, and then we do equal and opposite momenta after that. So you're pairing in this way, on opposite sides of these two circles on the Fermi surfaces. And this is the Fulde-Ferrell phase, where every quark pair in the condensate has the same net momentum 2q. Each quark has the p that cancels out plus a q that doesn't cancel. So 2 quarks in a Cooper pair, 2q. So the condensate now has position dependence. The condensate now looks like e to the 2iq dot x. So it's a plane wave. The condensate now looks like a plane wave in space. And so that's the Fulde-Ferrell part of this. The Larkin-Ovchinnikov part is to say, well, suppose you take a superposition of 2 of these with q in the opposite direction. So then I would be pairing strange quarks on a circle here, with down quarks on a circle here, just flipping the whole thing on its, in the z along the z-axis, and then I'd get e to the 2iq plus e to the 2i with minus q, and if you add those up, that gives you a standing wave, a cosine modulation of the condensate. So now you're looking at a condensate. It's not uniform in space. It's got some kind of spatial modulation, either just the phase of the condensate in the Fulde-Ferrell case, or a standing wave with the modulus of the condensate having nodes and antinodes and big condensate here, small condensate there, but with a definite momentum pointing in a definite direction. And that's coherent enough that you can still exploit the attractive interaction, can still operate here and lower the energy of the system.
In general, it's cosine plus sine with some coefficient?
Yes, yes. So I'm just choosing cosine here as some. I mean, yes, in general, you could have cosine plus sine, right? I think that's just like sort of shifting in space. Let's think. Let's see. I think you want either a pure cosine or a pure sine. I think if you add them up, that's going to, I'm not sure how you're going to, I guess you could have, okay, so you could have a phase difference between these, between the forward one and the backward one. Okay, right. Now, okay, so we started off with, two rings, one on the down and one on the strange Fermi surface. And then we said we could throw in two more rings here and here. And you might think, well, okay, we should be able to throw in more. How about rings to the side, right? Front and back. And you can add those in, and that's going to get you more interesting structures. So that's going to get you structures that sound more familiar, like a cubic crystal, okay, where you have plane waves, these sort of cosine plane waves in all three directions, right? Cosines in all three directions is going to give you a cubic structure with nodes on the edge of the cube and antinodes in the middle. Or you could imagine something more complicated that was face-centered cubic or hexagonal close-packed or, body-centered cubic, whatever you might want. Okay, so by building up these plane waves, by adding up different combinations of plane waves, possibly with relative phases, as Tetsuo was just pointing out, you could build up all sorts of interesting spatial modulations of this condensate. Now, this makes doing the calculation of the energy much more complicated. Previously, we thought, we were very proud of ourselves before. The condensed matter physicists only have a 1-by-1 condensate. It's just electrons, right? And we thought, oh, we're so much better. We have 18-by-18. We've got 9-by-9. We've got 3 colors and 3 flavors. That's way more complicated. Well, now, if you throw in momentum, that's a whole other set of labels for these condensates. And it becomes an even bigger, more complicated condensate. So that makes the calculations very difficult. And so I'm not going to talk about how you do those calculations. You just have to deal with very big matrices. But so here are a couple of examples of where people have tried to evaluate which of these different possible sort of crystalline structures are the most energetically favored. And so here, what they're doing is they're looking at what's the stress on the pairing pattern. Here on the left, it's written as the thing that we talked about before, ms²/mu. If the strange quark mass is small down here, then there isn't much stress, and the lowest energy thing is color flavor locked. But as you increase it, color flavor locked energy goes up, 2SC energy goes up. And in this calculation, done quite a few years ago now, using the Ginzburg-Landau theory, the effective theory of the Loft condensate, we found that the plane wave, the two plane wave, the Larkin-Ovchinnikov phase was up here, but these two crystalline structures that were basically versions of body-centered cubic looked energetically very much favored. This is the energy here. So they looked like they were really going to win. So as you turned up the strange quark mass, or alternatively starting on the right-hand side, as you turn up the density, then there's a whole region where you'd have some sort of cubic crystal structure. And then finally, at very high densities, when the strange quark mass isn't important anymore, you'd switch over to some sort of color flavor locked phase. Now, this was kind of a audacious, shall we say, calculation, because you're using the Landau-Ginzburg theory which assumes the condensate is small. So that's really only valid near the phase transition where a second order transition where the condensate is just beginning to happen. And here that's not true at all. These condensates are big. So this calculation was, an interesting thing to do, but not very trustworthy. So these people here, some years later, did a calculation where they used a Nambu-Yonah-Lacinier model for the interaction between the quarks. And they then did a brute force diagonalization of that enormous matrix, which now includes a bunch of different momenta. And they had to truncate it. You can't include all the momenta up to infinity. So they had to truncate these matrices and use, some approximations and some clever techniques to reduce the size of the matrix as much as possible, and then diagonalize it by brute force. So within that mean field model, which remember is not QCD, it's itself just a model, they got very different results. So the black line here is the color flavor lock phase, which is going to win. Again, this is showing you the amount of stress here, but in the different language. But eventually it's going to have the lowest energy if you go down to the low stress end. But they found that the Larkin-Ovchinnikov phase looked really good. That's the single standing wave, the cosine. Okay. They found that the body-centered cubic was not as good, although maybe up here it would win. There's an interval of densities very close to this transition here, it would win. And the Fulde-Ferrell didn't look too great at all. Okay. So the answer is it's very hard to do these calculations, and the different methods at this point don't agree. This method here may be a bit more trustworthy, but there hasn't been too much more work on this since then that I'm aware of, and it remains a somewhat uncertain question which of the crystalline phases is the best option when you're at densities where the strange quark mass is creating enough stress, enough separation of Fermi momenta of the different flavors to stop just simple color flavor locking from happening.
So is there any analysis of the fluctuation? Because this 1D structure in LOYFF should be unstable, right?
Yeah, right. So no, I mean, I think just doing it at the mean field level was already hard enough. I agree. In one dimension, if it's effectively a one-dimensional condensate, and you'd think that would be disrupted on long distances by fluctuations. So yes, I agree. That's a very good point. And yeah, as far as I know, that hasn't been addressed. Yes.
Can you remind which is like LO and which is FF?
Yeah, okay, I'll go back for that. Here we go. So Fulde-Ferrell is just the e to the I QX, and Larkin-Ovchinnikov is where you have two of them. So the modulus of the condensate actually gets bigger and smaller and has nodes and antinodes.
Okay,
Whereas Fulde-Ferrell is just a phase modulation. So they're saying that the Larkin-Ovchinnikov is better. And you could guess why. It's because the Larkin-Ovchinnikov is using more of the phase space near the Fermi surface. It's using twice as much, right? So you would guess that it might be a more favored option. But you might equally have guessed that body-centered cubic, throwing in more of them in all different directions, would be even more favored. And yes, there are places where the circles may overlap with each other, and those parts cost you a little bit. But you'd think that gaining a whole circle would outweigh losing some little points. That's what we thought. We were one of the other group, right? We thought that some sort of more complicated thing would be favored. They didn't find that, and I can't see into their calculation well enough to understand why.
What about like competition between like other like single flavor like pairing?
Yeah, so there are other possibilities that I mentioned back here. Single flavor pairing where you can do color spin locking instead of color flavor locking. You can have meson condensates. So you'd want to throw all those into the mix as well and compare everybody.
Yeah.
Right. So here I'm just talking. Well, some of them are in here, right? There's CFL with K0 condensation is in here. Okay. So okay. So finally on this topic, people have thought a little bit about if you had one of these crystalline color superconductors, what would its properties be? So you can estimate what would its shear modulus be. What you're interested in is, okay, it's a crystal. How strong a crystal is it? How hard is it to deform? Because that's going to be a measure of how much impact it might have on, let's say, making a not spherical part of a neutron star. Could resist gravity. So they're very strong. So the rough estimate based on this was based on the Landau-Ginzburg theory, so again, it might be a little bit, dubious, was that the characteristic scale of the shear modulus was in the sort of MeV per cubic Fermi range, whereas for a nuclear matter crust made of ions, it's in the keV per cubic Fermi range. So this was this paper that made this estimate of the shear modulus of the Loft crystal. So, that's interesting because it means that if those crystals formed, they might be very sort of strong and difficult to deform, and they might preserve sort of memories of the shape of the region that they came from. There's also been a very rough estimate of the pinning. I think these same people did a rough estimate of the pinning force of a superfluid vortex, because that's what would come up in glitches. And the rough estimate was that the pinning force, so how much is a vortex pinned to one particular place in the crystal, was that it was similar to in a conventional neutron star crust, but that was just a dimensional estimate. So I don't want to emphasize it too much.
So the difference between nu QM, nu MS is the difference between electromagnetic and the strong interaction, is it?
I think basically, yes. I think in this case, in the case of the nuclear crust, it's just, an electron background supporting charged ions. And in the case of the quark matter, it's strong interaction driven. That's right. Yeah. Okay, so this, I think, is the end of what I wanted to say. Yeah, okay, what I wanted to say about the crystalline color superconductor. So my next topic is going to be a mixed phase. Okay, I see a question in the chat here, actually, about would it happen in the early universe? Yes, unfortunately, the early universe is much more in the hot range and much less in the dense range. So if you look at where it is on the phase diagram, it's sort of top left-hand corner. So unfortunately, the early universe is not conducive to the formation of any kind of ordered structures. That basically there's too much entropy per baryon, and you can get quark-gluon plasma, but you're not going to get not Cooper pairing of any kind, unfortunately.
But then you expect to find these crystalline structures in the center of Neutron Star.
That's right.
The core.
That's right. So the idea would be in the middle, you might have color flavor locked in the middle, where the density is highest, and so the strange quark isn't making much difference to the Fermi momenta are big. And then as you go outwards and the density drops, you might have a layer of this crystalline color superconductor, and then you go out from that, you might go back to normal nuclear matter or something like that. So it would give you an interesting sort of inner crust, so to speak, inside the star. Yeah.
The real core is the flavor, color flavor.
Well, I mean, or it could be just a crystalline core, right? That you never get dense enough to make pure color flavor locking. Or of course, it could be you never get dense enough to make quark matter at all, and the whole thing is just neutrons and protons. We simply don't know, because that red line in that thermodynamic plot, we don't know where that red quark equation of state line is. We don't know when it becomes favored. Yeah.
I have a nice question. So in terms of like Ovchinnikov like effective theory near the like Fermi surface, so all the like interaction, like 4-point Fermi interaction, so the 4-point Fermi interaction with opposite momentum is only relevant interaction, and then the unequal like momenta are like sort of irrelevant in a sense of renormalization groups. So how can this how can we like understand that from this RG perspective?
Yeah, I'm not sure how it works in the RG in that approach. So that channel is still going to be the most attractive channel, but somehow I don't quite know how in the RG approach the mismatch of the Fermi momenta comes in, that obstructs that channel, and then you have to look for alternative channels. And this happens, even if you didn't look at Cooper pairing with net momentum, you'd find other things like single flavor pairing, which had non-zero angular momentum or something like that. But those would be sub-dominant channels, which would also be attractive, but not as attractive. And it must be that if you include momenta, there are channels that are still attractive. Right. And somehow, the bit that I don't know is how does the separation of the Fermi momenta due to the strange quark mass I guess that you have two different Fermi surfaces, and so you're not sure which one to evolve towards. So you have to kind of redo the formalism a bit.
Right, that's true. In the case of like single flavors, so that's
yes, there it's clear enough.
Yeah.
But here, because you've got two Fermi surfaces, I think that complicates the whole idea of flowing to the Fermi surface.
Right.
Okay. Good.
Sorry.
Yeah, yeah.
So any, I think, evidence of the FFLO on this part? I think there are some experimental.
Yeah, I think there is evidence. It's difficult in condensed matter because they can't stress the flavors so easily because they don't have flavors. So they have to look at stressing the spins with the magnetic field. But then, superconductors tend to expel magnetic fields. So I'm still not sure how maybe they have different bands that act like different flavors. Honestly, I don't know. And I would have to go consult a condensed matter physicist. Okay, so let me go on to the mixed phase at the nuclear quark interface. So this is something where you've heard of it before, perhaps. People have different words for these things. They call them the Gibbs construction, or charge-separated phases, or pasta phases is what they call them when they're at the nuclear core crust interface. So I'm going to explain what one of these phases is, what the Gibbs construction is, because it's generic to all these situations. So just to remind you, what's the situation we're in here? We're thinking of the conventional hypothesis now, a hybrid star with a nuclear matter mantle and a quark matter core. So we've got these two curves here, nuclear matter and quark matter. Now we have to look at some of the small print, okay? The small print says these are neutral phases, okay? So this green line here is the pressure of neutral nuclear matter. And this red line here is the pressure of electrically neutral quark matter. And at this critical pressure, they have the same chemical potential, and that's where the transition happens between neutral nuclear matter and neutral quark matter. Okay, that all sounds fine. Why wouldn't you have neutral matter? Well, the complication that can make this interface here a little bit more interesting than just a bare surface where you switch from one to the other. The complication is that in order for a phase to be neutral, the electrostatic potential has to have the appropriate value. And it may be that the value of the electrostatic potential in nuclear matter that's neutral is different from the value of the electrostatic potential in quark matter when it's neutral. Okay, so when you have this switch over from neutral nuclear matter to neutral quark matter, that may also require a jump in the electrostatic potential, okay? And the presence of this additional conserved quantity, the electric charge, and in this case with an associated electrostatic potential, opens up the possibility of what's called a mixed phase or a Gibbs construction. So let's see how that arises. So here I've introduced the electron chemical potential, which is the same as the electrostatic potential. Because in this context, the only charge that the electron carries that we care about is electric charge. So this is the electrostatic potential here. And here up the side here is the free energy, which is minus the pressure. So the state with the lowest free energy is the favored state. And if we sit ourselves, I'm going to go back for a second, excuse me. So we're going to sit right at this point here where neutral quark matter and neutral nuclear matter have the same pressure. Okay, so they can coexist. So here we are, in terms of of electrostatic potential, here's neutral nuclear matter with the electrostatic potential that makes it neutral, and it's got the same pressure as neutral quark matter, which has whatever electrostatic potential makes it neutral. Okay, so they've got different electrostatic potentials here, but with those different electrostatic potentials, they can coexist. Okay, so far we're just looking at 2 points on here. This point here, neutral nuclear matter. This point here, neutral quark matter. Okay, but now, nature doesn't just look at that. Nature looks at all the possibilities. And what you see here is, supposing you looked at quark matter that wasn't neutral, supposing you increased the electrostatic, this is the electron chemical potential, so it's actually the negative electrostatic potential. It's a potential that favors negative charge. So here, you'd be making your quark matter a little bit negatively charged. Remember, the slope of this is the charge, right? The charge is d free energy by d electrostatic potential. So so here you've got negatively charged quark matter, And what you see is its pressure is going up and its energy is going down. In other words, the non-neutral phase is favored. Okay, and you can just imagine this. Just imagine a gas of electrons, right? No electrons has zero pressure. Some electrons has some pressure, right? Roughly speaking, you introduce more of the charge, it increases the pressure. But of course, normally that doesn't happen because you can't have charged phases in bulk. So you have to be neutral. But in this case, you can have some charge because, okay, this is negatively charged quark matter if the chemical potential is going along here. At the same chemical potential, what's going on with the nuclear matter? Well, at that chemical potential, you're deviating away from neutral nuclear matter, but you're deviating from it this way, and now you're making charged, positively charged nuclear matter. Okay, so if the chemical potential isn't at the value that makes nuclear matter neutral, and it isn't at the value that makes quark matter neutral, but it's somewhere in between, then A, neither of them are neutral, but they have opposite charge densities, and B, it's more favored because they both have lower energy or higher pressure. So this is why you get a mixed phase. The system says, oh, look, instead of having neutral nuclear matter and neutral quark matter, I can do charge separation. I can have negatively charged bubbles of quark matter surrounded by positively charged nuclear matter, and at least in terms of the bulk energy, they will both be more energetically favored than they were when they were neutral. Okay, so this is the sort of, this is the big physics point here, right? This is why mixed phases happen. It's because for each individual phase, you can raise its pressure by letting it deviate from neutrality. Remember, neutral means you're at a maximum of this function. It's when the energy, d chemical potential is zero. So neutral is when you're here at this maximum, and deviating from neutrality always lowers the energy or increases the pressure. So this is great. Now we can make a mixed phase where we have different regions of space, some of them with positive charge and negative charge for these two different phases, intermingled with each other. And that will be fine apart from surface costs, right? Now the bulk energies are all favorable, but the surface costs may kill you. So what are the surface costs? Well, there's electrostatic energy. We've made electric fields now, right? There's electric fields between the positively charged bits and the negatively charged bits. So there's electric fields all over space, and there may be surface tension. We've got interfaces between nuclear matter and quark matter. We were going to have an interface anyway, but we've got more interface now because we've got a whole bunch of, domains with surface. So the question then is, who wins in this battle? Are the surface energy costs big enough so that it doesn't form a mixed phase and it just jumps straight from neutral nuclear matter to neutral quark matter? Or are the surface energy costs small enough that you get some mixed phase? Anybody want to ask a question here? Because, this is the physics that I really was hoping to, illuminate for you. Yes.
Just check. So neutral nuclear matter, you say it's a neutron, a little bit proton, and then electron, right?
Yes.
And then altogether neutron.
Right.
And so when you say positive charge nuclear matter means neutron, proton, but the electron
Fewer
less.
electrons, right? We've turned down the electron chemical potential, so there aren't as many electrons and there are more protons. Right. Any other questions about this? Okay. So this is a generic mechanism. Anytime you have another charge like this, apart from the charge that controls the density that's changing as you go through the phase transition, if you have another charge, in this case electric charge, and it needn't be gauged. In fact, if it isn't gauged, it makes it easier. Then you will have the opportunity for these mixed phases. And another thing to notice is, to go back, supposing we weren't quite at this transition, suppose we were a little bit below it, so that the neutral nuclear matter was favored over neutral quark matter, that means you shift this green curve down a bit to say that the nuclear matter is a bit more favored. But even then, the mixed phase is better, right? So there's a range of densities around that first order transition where a mixed phase is favorable. Okay, so you can get it covering a range of densities. So this is a calculation that was done some years ago for the CFL quark nuclear interface, and this is the energy as a function of density as you increase the density. And at some point, this is without any surface tension at all, this black line here. At some point, the mixed phase becomes favored, its energy drops, and then as you go past the transition and up beyond it, it becomes harder and harder to make the mixed phase, and then finally, it's not favored anymore. And now, if you introduce surface tension, this is these families of lines going further up are surface tension of 10, 40, and 100 MeV per cubic Fermi. That reduces the range in which the mixed phase is favored. Here, it's only favored relative to the neutral phases in a smaller region, and if you turn it up to 40, it's never favored. You go straight from neutral nuclear to neutral CFL. And the different colors are different arrangements of the mixed phase. Is it droplets or rods or slabs? Those are the names that people give, pasta, like spaghetti and lasagna and so on. Okay. See what I want to do. Oh yeah. So my next final thing is to talk about another mixed phase, analogous, but instead of being nuclear matter mixing with quark matter, this is going to be quark matter mixing with the vacuum. But that can also be a mixed phase. So before I go on to that, does anybody want to ask a question? This last part is going to be pretty similar, right? Because it's another mixed phase. So you won't have to, do a whole new bit of understanding for this last part.
What is the realistic value of sigma?
That's a very good question. We don't know, right? What's the surface tension of the interface between nuclear matter and quark matter? That's really a microphysics Fermi scale thing that I don't know. You can estimate it dimensionally, but yeah, I just think we just don't know.
Origin of this surface tension, like physics origin.
Well, yeah, I mean, what is the origin of the surface? There's some sort of crossover, right, at the microscopic scale. And I mean, if you think of it on the model of a first order transition, you're going over a barrier between two vacua. And so going over that barrier costs you energy. But that's a sort of thermodynamic large scale view. On the microscopic scale, it could be something very complicated that I don't know what it is. Something involving, nucleons and quarks both existing simultaneously and doing something to each other. But we don't have a model of confinement, so we don't know how to. Yeah, I'm sorry, not a very satisfactory answer. Okay, so let me go on to this final mixed phase here, the strangelet crystal crust on a strange star. So now we're going to that other scenario that we talked about, the strange matter hypothesis, the sort of slightly out there hypothesis that nuclear matter, although it's what we're made of, is actually never the favored phase. It's always metastable. And really what nature wants to form is either vacuum or strange quark matter. So in that case, if you make dense lumps of matter, what it really wants to be is just quark matter all the way through with, as I said before, either a nuclear crust or the thing I'm going to talk about now is this strangelet crust, which is actually a mixed phase between the strange matter and the vacuum. So again, we're talking about a first order transition here between the vacuum and quark matter. But as before, the value of the electrostatic potential that makes the vacuum neutral, which is 0, right, may not be the same as the value of the electrostatic potential that makes the quark matter neutral. And so you'll have the same story again that we had before. So if the surface tension is low enough, I'll show you hang on, maybe I'll pop ahead here. So here we have the analogous picture to what we had before, except now we've got the vacuum here. And if you turn up the electron chemical potential in the vacuum, you get electrons, okay? And here's your neutral quark matter. And if you turn down the electrostatic potential in quark matter, you get positively charged quark matter. It's got fewer electrons, more up quarks, fewer down and strange quarks. So as before, you can say, oh, well, instead of going straight from neutral vacuum, if I come into the surface of this strange star from the outside, do I go straight from neutral vacuum and hit the surface and immediately I'm in neutral quark matter? Maybe, but maybe the system looks and sees, ooh, this charge separated phase is nice, both phases individually have higher pressure than if they were neutral. And if I mix them in tightly enough with each other, then you won't have too much worry about electric fields, although then you'll have a lot of surface to worry about surface tension. So again, you may get a mixed phase. And what is that mixed phase going to look like? Let's go back. It's going to be, instead of this sharp transition here, it's going to be little blobs of positively charged strange matter, also known as strangelets, with surrounding electrons. That's one way it might look. So basically, it's just like the crust of an ordinary neutron star. In fact, you could think of the crust of an ordinary neutron star as a mixed phase between nuclear matter and the vacuum, with electrons populating the vacuum. That's the liquid drop model, basically. So with surface tension and bulk energy and all that sort of thing. So, so with a student, we did an estimate of how thick a crust like this might be. And it depends very sensitively on the surface tension. But if the surface tension is less than this critical value, which appears to be about 10 MeV per square Fermi, then you can get crusts. It also depends on the strange quark mass. You can get crusts that are a kilometer thick. In other words, not so different from the crust of a regular nuclear matter star. So I can say more about how you obtain this. You use the Thomas Fermi approximation in a Wigner-Seitz cell, and there's all these boundary conditions, and you get this profile, but I'm basically running out of time. So yes.
Yeah. So in your figure, given in the previous one too, this positively charged, strange,
yes, strangelets. Yes.
They form a crystal?
Well, yes, you have a whole bunch of droplets, and the natural thing would be for them to form some regular structure.
Yeah.
Right?
Because of the Coulomb interaction.
Yes.
And then in the calculation of the energy and so on and so forth, it is included or it's not?
Yes.
Included?
So when you do the calculation of the energy, what you do is you draw a unit cell, right, with one strangelet in the middle, and then you say, okay, it really ought to be a cube, but that's going to drive us crazy. So we treat the unit cell as a sphere. Okay, and then in that unit cell, you solve the Thomas Fermi equation for the charge distribution with a strangelet blob in the middle and electrons outside, and you have various boundary conditions. You know, there's no electric field at the center, there's no electric field at the edge of the cell. The potential and the electric field at the surface of the strangelet are continuous. There isn't some charge trapped on the surface. And there's a pressure discontinuity across the surface of the strangelet because it's like a balloon. It's got surface tension. So there's some pressure inside it, which is related to the dimensionality d of the is it a sphere or a rod, and the size of the strangelet and the surface tension. So you put in all these ingredients. So you're taking into account the electrostatic interaction, and you end up getting some kind of well, where am I going the wrong way? Oh, wait a minute, going too far. You end up getting some kind of typical size of a strangelet at a given density. And so you can get an equation of state for this, and then you can put that equation of state into the TOV equation and find out how thick the crust is. So you do that. Yes, as I said, you get this profile within a unit cell. But okay, I don't think I want to talk about it in detail. So you get a whole family in the strange matter hypothesis. You get this family of objects that looks a bit like what we have in the real world. So if you have a very small, a light object, so this is the mass-radius relation here. Mass in solar mass is up here, and radius in kilometers here. If you have very low mass, then it puffs up, right? It doesn't, it's not under a lot of gravitational squeezing. So the pressure isn't very high. So it's all just strangelets with electrons in between. That's the strangelet equivalent of ordinary matter. Okay, and that gives you these strangelet planets. Okay, and then as you add more and more to the mass, gravity begins to compress it, and eventually you get strangelet dwarfs where you start getting maybe some, I think with the strangelet dwarfs, I think you might be getting some strange quark matter in the middle. And then at some point, it can't hold itself up against the gravity anymore. It collapses, and then you get a branch of strange stars. And this is exactly like what you get with nuclear matter. these are white dwarfs here. And these are regular planets here. There's a planet white dwarf branch for ordinary nuclear matter, which then gives way to a neutron star branch. And this is just the same thing except with strangelets. So, okay, this strangelet crust, it basically like the nuclear matter crust, except the strangelets have a lower charge to mass ratio because they've got strange quarks in there that can help you achieve neutrality without electrons. So, okay, they've got a lower charge to mass ratio, but otherwise similar. So, you know, some of their properties are not so different from nuclear matter crusts. And it raises the question of, could it be that a strange star with a strangelet crust could imitate an ordinary neutron star, and you wouldn't be able to tell the difference observationally? So, okay, now I'm going to go to my summary because I've reached the end of my time. So there are many questions on this topic, as you've probably already seen. You could ask about what should we be calculating for solid phases? You know, what properties of the solid phases are interesting for the purposes of seeing evidence of them out there in nature? I talked about shear modulus. You could talk about thermal conductivity, what temperature they melt at, the things that might be relevant, you know, in mergers and things like that. If you imagine two neutron stars merging and getting hot, and if there's a crystalline phase, when does it melt? You know, these are all things that one could look at. As far as the Larkin-Ovchinnikov phases go, there's the question that was already raised: which crystal structure is favored in competition with other crystal structures and other flavor singlet pairing patterns? And people also haven't sorted out how those Loft phases would interact with superfluid, because the phase itself could be a superfluid and have a crystal. So you can have vortices in there. The mixed nuclear quark phase, the second thing I talked about in a hybrid star, what I showed you was CFL quark matter mixing with nuclear matter, but you could look at other quark matter phases mixing with nuclear matter and get different looking answers for the mixed phase. And also, what is the favored form of the pasta? Is it slabs, you know, one-dimensional? Is it rods? You know, is it spheres? What is it? You know, depends on the surface tension. Ideally, you'd estimate this, you find out what the surface tension is, but we don't know how to do that. And the strangelet crystal crust, well, you know, could neutron stars really be quark stars with a crust? What would you look at? Cooling after accretion, X-ray burst oscillations, things like that. Could that tell you whether this is whether the crust is made of strangelets or not? One issue with that whole strange star hypothesis is the so-called strangelet pollution problem, which is that if strange matter really is favored, then there ought to be strangelets running around the universe, which would convert all the neutron stars into strange stars. And we think that we have evidence that some of them are in fact neutron stars. So not so clear, okay, but it's still an interesting idea to play with. Okay, so that's the end of my survey of solid forms of quark matter. Thank you for listening.
Thank you very much. Well, yeah, Motoi has.
Yes, so let me see. In the case of solid quark matter, due to the breaking of translational invariance, low energy physics, yeah, there'll be phonons, right? Then what happens to the transport? Yeah, right, I agree. So if you have a crystalline phase of any of these kinds, the first thing you look at in terms of the low energy behavior is going to be the phonon spectrum. Absolutely. So yeah, that's what you'd be looking at for that. If but what it would do, I don't know. You know, but yes, it's what you'd have to look at.
So you have a strangelet planet.
Yeah.
Planet.
So that's just that's where it's all crust, if you like.
Yeah.
It's just.
How can you make it?
Well, it's unlikely to be. I mean, I'm talking about what exists in the sort of theoretical picture here. What you could imagine maybe is that you know, two strange stars, each with a crust, collide, and they blow off some of their crust, and then you get some just strangelet crust floating around, which would be a sort of blob of strangelets, positively charged with electrons in between, bound together electrostatically, just like normal matter. And different sizes of strangelets would be like different elements.
Okay, so any other questions?
the discussion of the mixed phase, you assume the first order transition.
Yes, that's right. First order phase transition.
If the transition is crossover,
I don't think you can, yeah, I don't think you're going to get that. So here, it doesn't matter which of these pictures I used. It's sort of essential that you have two different phases here that are neutral with different electrostatic potentials. If you have a crossover, I think it's just going to cross over. But of course, you can go continuously from a crossover to a first order transition by making it tighter and tighter and tighter. And so actually, maybe it would be interesting to see if you make it really quick crossover, how quick does it have to be before something like this shows up? That is an interesting question. Okay.
So you show the mass radius relation for the strangelet crust.
Yeah.
How does it so as far as I remember, a pure strange quark mass passes through zero radius and also zero mass. I mean the origin in this plane. And
yes.
How does it make it different from that?
I mean, well, I'm not. Maybe I don't quite get your question.
I mean,
that's. I agree. That's in there. That's way down.
Yeah.
One strangelet is all the way down deep in the far bottom left. Right.
Yeah. Yeah. That's right. Yeah. So, but once you have a crust, then you don't pass through the origin. So what is it?
Well, it's. I mean, it is all crust. Like crust just is ordinary matter, basically. It's nuclei with electrons in between for normal stuff, and it's strangelets with electrons in between for strange matter. And you can have as much of that as you like, right? Small pieces are further down this curve with smaller baryon number, fewer and fewer strangelets. And then as you add more and more and more, you increase the baryon number, you add more strangelets. At first, it just expands like R cubed, basically, right? But then gravity starts to squeeze it. So at some point, it gets heavy enough that when you add more, it doesn't get any bigger, right? Gravity just squeezes it down. And then eventually, gravity wins and it collapses. And that's when the electron degeneracy, this here happens when the electrons can't hold themselves up against gravity anymore.
Right. Yeah. So the contribution of electron is important.
Yes, yes. Okay. If the electrons are driving really everything in this branch.
Right.
Yes. I mean, the strangelets are just basically funny nuclei with an unusual charge to mass ratio for this purpose. I mean, unusually small charge to mass ratio for this purpose.
The planet branch, if it goes to the very small mass, then it eventually goes to the zero.
Yes, it goes like M goes like R cubed, right? M is 4 pi R cubed times density. It's some form of iron, basically some sort of strangelet iron, blobs that get smaller and smaller.
So if you forget about the electron, then everything is neutral. Then it's starting from here, and then it's all R cubed, right?
Yes, I guess.
If you forget about electron and the neutral.
If you forget about, I'm not sure what to do if you forget about the electron.
UDS. Suppose you have massless UDS with strange matter, then it's R cubed. Mass is R cubed.
Yes, I guess then you'll, yes, okay. So then the compact branch here, I think, goes all the way down here. That's right. You don't have any of this stuff because it doesn't puff up like this. Right. Yeah, right. Yeah, that's right. Yes, that's what you see a lot in standard discussions of strange stars. But here, my point is just that, it can be more interesting than that. Right. You can get the strange equivalent of ordinary matter and white dwarfs and all that.
Okay, some question from the audience.
Let's see. Oh, yes. If low mass strange white dwarfs collide, would it lead to supernova-like explosions? Oh, that's an interesting idea. Gosh, I haven't thought about that. Or could they just undergo supernovas? I mean, they can be their own supernova, right? When they collapse here. Yes, I agree. I agree. You can revisit a whole bunch of ordinary matter, ordinary astrophenomenology. You can sort of revisit it, building everything out of strangelets instead. I don't have too much comment about it, other than to note, yes, the possibility is there.
So suppose we have a completely massless UDS. Suppose, and then do you still think?
No, then so let me go back to this. So if the strange quark is massless, then the chemical potential that makes it neutral is zero. The
Yeah.
mu. So then this red curve sits on top of the sort of cyan colored curve here, and then there's no room for a mixed phase. There's no motivation for a mixed phase because you go straight from neutral quark matter with zero electrostatic potential to neutral vacuum with zero electrostatic potential, and there's no jump in the electrostatic potential to motivate a mixed phase.
But you still don't know whether this massless UDS strange matter is really the ground state of.
That's right. You still don't know whether this red curve here
Yeah.
is high up and you get to it first before you get to nuclear matter, or whether it's over here somewhere. Right. You still don't. That's a separate question.
What determine? I mean, we usually use just a simple Bragg model or something.
Right.
Do you have any idea beyond that?
I mean, it's some sort of QCD arrangement of the vacuum that as you increase the quark density higher and higher and higher, you sort of disturb the QCD strongly coupled vacuum and change its energy. And the question is how much? And that's unfortunately a sort of, QCD high chemical potential problem. That's the kind of thing that if we could solve the sign problem, we would, yeah.
Yeah. Right. Okay. So no question from the Zoom audience? Anybody? Okay, seems not. Okay. So thank you very much.
Thank you very much.
And then